So hello everyone, thank you for coming today for my talk about functional programming in Kotlin and also a little bit of Java. So this talk won't be like really serious, but the topic sounds like really hot. So like, why do we even need functional programming? And I really like that you came here, even if like functional programming sounds like really scary and has a lot of myths like, do I even need PhD to write code in functional style? Or maybe as a regular software engineer, I can do that, or maybe not. So today we will discuss this and let's see how it goes. So like a little bit about myself. So my name is Karin. I'm working at CircleCI as a senior software engineer. I have a background in like really different languages in Kotlin and Scala, both on front end and back end. Right now we are doing Clojure and Golang. So my experience here will be based more on like my previous job places because I can compare Kotlin and Java to Clojure, but not so much to go. I am living in Potsdam, a city not so far from Berlin, and I have 2 lovely cats. And a fun fact about me, so like multiple times after giving my talks online, I had reviews for my talks that stated, okay, I have no idea what Kotlin is, but the speaker has nice cats. So I really think that you need to see them. So like this is Casper and this is Edison. So let's get started. So the question is why we are even talking about functional programming. And I have multiple reasons for that. So first of all, it's a really hot topic for every person in software engineering, like both software engineers in general, conference organizers. So for example, the initial idea of this talk happened after speaker lunch because we were talking about random stuff and one of the conference organizers told me like, I can show people talks about like abstract fabrics with abstract fabrics inside like internals of the JVM, like everything that should be like really scary. And everyone like, sure, like no one bats an eye, but should I add a word monad in the title talk? And everyone is like losing their mind, like, oh no, like monads, no, I'm not going to this talk. It's like way too difficult for me. And I think that's not true. Like, I had an experience of explaining the people from Java, like really enterprisey background, like how to use Kotlin, and especially functional Kotlin. And I'd like to present my findings and hopefully make functional programming less scary for you. So the agenda for today is elements of functional programming. So like what parts of functional programming do we even have? What can we use in our day-to-day programming? What can we even call functional programming and why do we need it? Monads. Error handling as like something that we are doing on the day-to-day basis. And a little like closing discussion where to use functional programming, where not to use, and some folks on this topic. So I will show you the examples of functional constructions in Kotlin and Java. Initially, this talk was oriented on more JVM languages, but since we are on Android conference, I decided to keep the talk only to Java and Kotlin as more relevant languages. Here, I should add a small disclaimer that I am personally more backend-oriented software engineer, and the only thing about Android that I know, like, don't run heavy calculations on the UI thread. And that's it. So my perspective may be like more oriented towards backend, but I feel like it will be useful for every Java and Kotlin developer. So elements of functional programming. Why I am calling these elements and not just functional programming? Because like it's not like whenever we are talking about object-oriented programming, every software engineer is doing like really the purest object-oriented programming. The same holds true for functional programming. Most of the time we are mixing up the styles whenever it fits or like style or task or like our view, which is why I am calling it elements and not functional programming. So like, why are we even having different styles of programming in general? Well, because for every engineer, the most important problem, or like one of the important problems, is complexity. So, and every style tries to solve it somehow in a different fashion. So whenever we are talking about, for example, object-oriented programming, we are trying to scope our complexity to something like classes. And for functional programming, we are trying to orient our style to, for example, immutable structures, or like having no global state. Like as you can see on the picture, statelessness is one of the core concepts. Another important concept of functional programming are functions itself, which are stateless, and they are lazy, which means typically we are only executing or like running a function only at the time when we really need it, and before that it waits for us and waits when we will actually need its result. So pure functions, I will go through the pure functions on the following slides, and side effects also. So let's take a look on pure functions. So a pure function is a function that that whenever you give some kind of input, so like fixed input, you will always, like input x, you will always get the output y for that. So as an example, like the function +1, we are passing as a value to this function 5, and we are pretty sure that every time we are passing 5, we will get 6, and the same holds for every possible valid input. So no side effects. Like side effects, like is something that is outside of our control. Typically, as a side effects, we are considering, I don't know, writing something to a database, because it's outside of our control. So the database may disappear, may not exist, like AWS may be not available. So it's something outside of our control. And technically, writing something to a console or like to a file is also a side effect. So technically, writing logs is like not so pure. And this is the problem, or this is exactly why I told you that we are like imagining functional programming as some ideal concept. And the same is for the pure functions. We are like striving to the pure function whenever it fits, when we can scope our calculations to something tiny. But like we cannot really say like, okay, we are implementing all our ideas or our projects without database, or like, no, I'm not writing logs anymore. That's not pure, sorry. Like auditors, like business, I am really sorry, but I cannot. It's against my views. No, like we are not doing this. We are doing the best in our interests and trying to compromise, but they are keeping in mind that purity is important, but not the like really target for us. So this is about the functions. So like, yeah, we are not altering and not depending on like some kind of global state, keeping it local. And for structures, like important concept of functional programming is immutability. So all the languages have different views and different mechanisms that add immutability to them. So for example, for Java, we have a framework or library called Waver, and in the standard library of some versions we have records, final modifier, In Kotlin, we also, from libraries and frameworks, we have arrow and like immutable collections. So for example, Kotlin X collection immutable, like read-only, so like var and val concepts. And the most important point here is not every type of immutability is the same as the other ones. There are various types of immutability. So for example, if we define in Java something like that, so like we are declaring a list using arrays as list, and we cannot say like, okay, this reference should point to a new one because it's, yeah, final. But in arrays of lists, we can actually change the elements inside. So it's like more reference immutability, but not like a guarantee for the content being the same as we put it and left it here, because somewhere, like, I don't know, in another thread or like in another function, it may be changed, and yeah, we are only seeing the same reference, but not the same content. It's not guaranteed. So from the types of, like this is for Java, and for Kotlin, we have 3 types of like collections and their immutability properties. So like you cannot modify, but someone else can, like totally immutable, and guaranteed, like nobody can modify collections or lists. Also, what's important, like for previous slide, is like while we can wrap in Java, for example, in unmodifiable list, but yeah, the deep structures are not covered. So for example, imagine you have a list of lists. Well, while you can say, okay, like the list holds those references, but yeah, the inside contents may be changed. So we are only covering non-nested structures. Okay, so if we cannot modify our collections, is there something that we can do with them? So we can produce the newer one based on some transformations or modifications or selecting a subset of elements from this collection. And let's take a look at the typical functions that we are using for that. The first one and the most important is map. It's a simple transformation, so like every element is mapped or transformed one by one into another one. So like this, we're transforming all the frogs into unicorns. So for Java, what's interesting here for all the functions, I think, or almost all, is they are added via Stream API. So to wrap it back into the collection, you have to do something like toList, for example. So keep in mind that, and in Kotlin it's pretty straightforward. You're passing a lambda and you're getting a new transformed list with unicorns. That's for map. And if we already have a mix of unicorns and frogs, we can filter them. So I don't really like the name filter because it's always hard to remember, like, do you get as a result the items that match your predicate or like those that don't match? So like in Java, Kotlin, I think in Scala, Groovy, and Clojure too, the concept of filter is like it's a keeping filter. So you're getting only the items that are matching your predicate. So again, same for Java, you need to collect them back. And for Kotlin, it's pretty straightforward, saying, okay, we need only items that are unicorns or like animals that are unicorn or like frogs. And we're getting a new list only with them of newer size, like that is equal or smaller than the original one. Fold. So fold is some way to, like whenever we have a collection, we are doing some operation and collecting them using some transformation into a single element. So, for example, you have a list of, I don't know, letters. And using fold, technically, you can collect them to string like ABC, like with plus AB, ABC. So fold in Java has an operation that you need to pass, and also a starting element called accumulator. So for, I don't know, collecting a string, we are doing like it's empty string, or like whenever we want to make a sum of integers, we are starting with 0. Here, the syntax for Java is a bit different from the other ones, and it accepts collector. So like it's not doing fold, but collects. And collector is actually a for function. So for example, there is a predefined collector called collectors to list, which just collects the elements to list like just straightforward, in a straightforward fashion. But technically you can define your own. Collector is typically consisting of for functions called supplier. So like the starting element, reducer, that explains how to add to the existing one. In the next element, merger for combining two intermediate calculations into one, and finalizer. For example, you can imagine a useful finisher, sorry, not finalizer, like string builder to list, for example. And the last but not least is flat map. Flat map looks almost the same as map. The only difference here is we are finishing or mapping with elevating our elements on the same level, so like flattening. So if as a result of our transformation, for example, we got like lists of lists, we are like, okay, flattening them, and all the elements, instead of being on the separate lists, will be elevated to a level upper, so like they will be on the same list. So like box of boxes, we are removing the smaller boxes and put everything together into bigger box. Again, nothing really special here. Looks almost the same as map, but also has more additional actions. Flat map will be useful for our next topic, but in a not so obvious way. So let's introduce our next topic called monads. So like monads are really, really simple. Like everyone knows that a monad is just a monoid in the category of the endofunctors. So like now what? The problem with this is like every Scala meetup starts with some definition like this, and like no one really like most of the people like don't really understand what does it even mean. So like the penguin says thank you. Like I don't know what to do with that. So and I'll give you a simpler explanation of how can you understand the monad. It won't be like really academical, but it's like really, really simple. So like do you know monads? Like maybe not really. Are you using lists? Well, that's a monad. So and why is it even a monad? So a monad is just a type, an instance of which can be created and which has a flat map function. So that's quite simple. So based on this idea, a list is actually a monad. So, and you're using monads on the day-to-day basis. A flat map function is not the same for every type. So for the collections, or like more specifically for lists, we've seen it on some of the previous slides. But you can actually define a flat map for other types. And we will return back to this topic later. So I have to admit that in the standard library of Java and Kotlin, you cannot really directly benefit from monads. You can using Waver and Arrow, but for the standard library like of Scala, there are already a lot of monads, and you can use this flat map already for your calculations, but not in Java and Kotlin. But let's pinpoint this flat map and monads topic here and return to it a little bit later. And let's go a little bit back for coming to flat map back via error handling, something that we are doing on the day-to-day basis. So let's return to it, like everyday programming, no functional programming, nothing. So like whenever we are writing a Java code and something may get wrong and we want to show that, we will typically write something like, if something is wrong, throw new exception, and that's completely fine. Later, somewhere in our code base, we will handle it in the method signature. So that's also absolutely fine. And whenever we will call or like work with our function that typically throws or that may throw an exception or like some error, we'll wrap it into try catch syntax, and that's also absolutely fine. So, but imagine I am like a developer that wants to use some more modern Java, I don't know, like Java 8 or something, and I want to use my function in the Stream API. Like, the question is, like, can I do that? And the answer is, like, not really. Like, we cannot just say, okay, our function throws a checked exception and then put it into the Stream API, so that's not working. If we want to do that, we can theoretically put try-catch block here, or, I don't know, typical approach for this problem is wrap the function with a checked exception into a function that doesn't throw a checked exception, and then unwrap it back. That's not really convenient because sometimes I'd like to know like what exactly went wrong, like right in the place, and here I have to derive it somehow. So what are other languages doing with this problem? So for example, Kotlin has no checked exceptions. So like no checked exceptions, no problem. If it's good or bad that there are no checked exceptions in Kotlin, so like it's up to you. It's a really hot and debatable topic. So in Kotlin, I will just write something like this out of the box, and it's working. The problem is the exception or something may go wrong here anyway, and I cannot really see from this exact function that it may happen. So what can I do in this situation? So like for simpler errors in Kotlin, we are typically saying, okay, either we will have a proper result from the function or just a null. like to internal, if we are passing like a letter, we will get null, and if the number is like 42, it will return our 42. But we don't really can see the difference between multiple error paths. For example, if we are passing a character, or we are passing a technically long, not int. In both cases, I think we are getting nulls. And sometimes we want to differentiate the error cases. So what else there is in a standard library of Kotlin? There is run catching. The run catching is a block that will consume all the errors, all the exceptions, so everything throwable, and then you deal with it in a various fashion. So I cannot really, like, I personally don't like run catching because it catches everything that is like has been thrown. And in my practice, there were some interesting cases of run catching out of memory error. And I don't really personally like it. So what else? Sometimes we have the situations when we can say, okay, there is a final set of the outcomes. For example, I am an investor, and like everyone knows that I can either successfully invest or definitely lose money. So there are only two outcomes, and we will define the happy and unhappy paths into our domain model itself. So this works if you can list all of them, but yeah, not all. This is like not a one-size-fits-all solution. And what's interesting here, if you have just only one happy path and multiple like error paths, there is a pattern called either that we can use for our error handling, and that we are typically using in functional programming too. So, for example, if we have multiple validators, for example, for transaction of money, we have some like user ID, like target ID, and the money sum. We know that all of three items can be invalid. And we can say, okay, like we either successfully transferred money, or like one of three or all of three items for transferring money were like wrong or something. And for the cases like that, we are using either. So either is added in Kotlin and Arrow using the libraries var and Arrow. And they look like this, so like pretty simple. Either is characterized using two types, left and right. And the mnemonic here is right. And the right side value is typically some kind of success that you are expecting. And on the left, there are various errors. So, like, so as you can remember, a monad is something that can be created and has a flat map function. And the thing is, either also has a flat map function. And for getting, for example, your historical data for stocks, as in this example, you can flat map them, so like you can chain multiple eithers using flat map. So like, how does flat map work for either? Whenever our either in our chain becomes left, we are stopping our execution and saying, okay, the final result of this chain is left and our last value. But whenever we are ending up with right, we are saying, okay, we are continuing with this right value. So I told you that Kotlin and Java are not benefiting directly from flat maps and monads as in Scala, but Arrow, for example, fixes this issue and adds a pattern called monad comprehension. So this example using flat map may be not so readable because the more flat maps we are getting, the more Hadouken-like our code may become because there's more and more nested flat maps. And monad comprehensions looks pretty simple in Arrow. In various versions of this library, it looked a bit different, but in the current one, for example, we are defining an either block telling, okay, here our context is either. It can be also be something other, so like null or optional. But the most important one for error handling is either. And as you can see, the bind function. So the bind function does almost exactly the same as flat map, which says, okay, if this execution will lead us to the left, so like we couldn't get something from the database, we are dropping our execution and saying, okay, left. And if everything works out, we are just saying, okay, let's continue in our either context, executing our queries to the database to get the end result. So that is the pattern of monad comprehensions. And when you have a long chain of like queries that you, for example, need to do to the database, it's quite convenient to say, okay, we will handle them in bulk. So to the conclusions, so like the good news is you're already using elements of functional programming, so like lists or monads, for example. A lot of you, I think, are using map or flat map function, so like great. Whatever adopting a functional programming style, consider the support of the libraries, because some libraries are not so working well with either and require like explicit try-catch, and you will have to adapt them somehow or just deal with it. I'm not sure about Waver because I haven't used it personally, but it looks really promising. But Arrow was great, so we used it for a fraud detection service, and there are like no real big downsides to the performance. And we use either a lot, and it's a library in an active development, so I can strongly recommend it using in your project. So another important thing is like consider team knowledge, because while you can introduce your teammates to the monads, it's like not so difficult. The problem sometimes is you have strict deadlines, and sometimes you still have to compromise as an engineer and stay in the domain of knowledge that you are already having. So sad but true. And about performance and immutability being slowish, well, that's an interesting point to consider, because in my understanding, if you're experiencing like really like performance issues using functional programming in Java and Kotlin, maybe Java and Kotlin are not so like the instruments that you are really needing. And for benchmarks, for example, typically people compare sorting algorithms, and the problem here is like it's not like you will write the same code in a functional style, in object-oriented, it will be something completely different. So that's all. That's my all concerns here. And I strongly encourage you to use maps, flat maps, monods, and others when you can. So thank you for coming to my talk. And I hope monods are not so scary anymore for you.